Okay, go ahead, Group B, please. Group E, don't be shy. Group E, don't be shy.
Hello.
Hello, hello, hello.
These two figures answers the first question in text 1. The figure on the left shows model performance, including accuracy and macro F1 for different window lengths. We can see that performance generally improves as the window length increases, although macro F1 shows some fluctuations, especially at the 5-second window. This suggests that longer windows provide more temporal context, which helps the model better recognize activities. Overall, the best performance is achieved with the 10-second window.
Okay.
And the figure on the right shows the training time for each window length. Interestingly, the training time decreases as the window length becomes larger.
Because
This is because
go ahead.
longer windows generate fewer total training samples,
But that's
which
the thing.
reduces
Listen, you should have strides, right? You should do like when you do convolutions, right? You should have strides. So otherwise, it's kind of silly, right? You know, when you do convolution, you have stride in the convolution, right? So you shouldn't implement it with strides, right? Yes.
Yeah.
Okay. Go ahead.
And from these results, we conclude that increasing the window length improves performance, while also reducing training time in our experiments. The 10-second window provides the best overall trade-off, and we don't observe a clear point of diminishing returns within the tested range. And this figure answers the second question in text 1. The x-axis represents the prediction horizon, which is how far into the feature the model tries to predict. The y-axis shows accuracy and macro F1. We can see that both metrics decreases as the prediction horizon increases. And when the horizon is 0 seconds, the model performs best because it's predicting the current activity. At 0.5 and 1 second, the performance drops gradually, which means the model can still make useful short-term predictions. However, at 2 seconds, the macro F1 falls significantly from about 0.63 to below 0.5. And this indicates that the model can reliably predict activities up to about 1 second into the feature, but performance degrades substantially when the prediction horizon reaches 2 seconds.
Okay.
And the figure answers the third question in text 1. In this chart, we compare the macro F1 score under several missing data conditions, including random point dropout, black dropout, and channel dropout. We can see that the model is fairly robust to moderate missing data. When the dropout rate is low,
this is so different from. So when you have the accelerometer channel, do you drop all the accelerometer channels or just one by one? So because the accelerometer has 3 channels, right? X, Y, Z, correct? So when you drop the accelerometer, do you drop all the channels or just one? How do you drop the channels in the accelerometer? Can somebody tell me? Because I don't believe this one, right? Because if you drop the gyroscope, of course, nothing changes, right? But if you drop the accelerometer, then yeah, it should be pretty bad. Also the other groups, right? The other groups show that if you drop the accelerometer, then the performance drops. So unless you, tell me how. Yeah, tell me a little bit.
We can see that the model is fairly
No, but my point is not
robust
consistent.
to
No, it should
moderately.
not be. It should not be. If you drop the accelerometer, right, the performance should drop to 0, right?
Oh,
You see, also you saw the other groups, right? The other teams, they showed you that if you drop the accelerometer, first of all, the accelerometer is 3 channels. So what do you drop in the accelerometer? All 3 channels. What do you drop? Do you remember?
no.
Then if you present something you cannot answer any questions, then what is your boss gonna tell you once you go to once you have a job? If you present these slides to your boss, right? And your boss asks you a question and you don't answer, what's gonna happen to you?
Oh.
Huh? So of course this slide doesn't make sense, right? Go ahead. Show me the next one.
The next one. Okay.
These
2 figures answers the fourth question in text 1. And the figure on the left compares the macro F1 scores of GRU and CNN models using 2 window lengths, 50 and 128 samples. We can see that the CNN with a 128 sample window achieves the highest macro F1, slightly outperforming the other models. And this indicates that both the model architecture and the window size affects performance. And the figure on the right compares the training time of the same models. Models using a 128 sample window train much faster than those using a 50 sample window. And the CNN with a 128 sample window is the fastest of all. And from the results, we conclude that a relatively simple CNN model is sufficient for this task.
Okay.
CNN with the 128 sample window provides the best overall trade-off between accuracy and computational cost.
Okay. This slide answers whether sensor drive and output info. I use a GRU model.
Right? Did you say? What did you say?
I mistake the sheet. Let me restart. I use the GRU model chain in test 1 and extract window level embeddings from the model. Then for each subject, I average the embedding within each activity and concatenate these activity level averages into one subject vector. And I construct 4 subject level features from activity labels for label derived. These include activity proportion, average segment duration, transition frequency, and the dynamic static activity ratio, and apply agglomerative clustering to separate the 2 views and UMap for visualization, and evaluate the consistency between the 2 cluster results using AI and NNI. 好，下一页。
Wait. What is UMAP? What is UMAP? What is UMAP? Tell me what is UMAP.
I will showing the.
Okay. Very good.
Showing, yeah. And this slide answer whether sensor derived and label derived embeddings produce similar subject clusters. The ARI is 0.09 and the NNI is 0.239. Both values are.
What is ARI? What is NMI? Tell me.
Exactly, I didn't deep research about them, but I think
again, if you're presenting to your boss and your boss asks you a question, what's going to happen to you if you cannot answer? Go ahead.
I'm sorry for that.
But it's,
Oh.
it's not for me, right? I'm trying to make the point that if you just let the Gen AI do everything, right? Then when you do a job and your boss asks you what job you did, then you have no answer. You did no job, right?
Right. Okay. Both values are relatively low, which means the two clustering results are not highly consistent at a global cluster level. However, the mean nearest neighbor overlap is 0.43. This suggests that there is still some local similarity between the two embedding spaces. In other words, some suggest they are close in the close Holes in the sensor-derived space are also closed in the label-derived space. Overall, the two views show only partial consistency. The label-derived embeddings mainly reflect activity level statistics, while the sensor-derived embeddings may capture additional motion patterns within the same activities. Okay, 下一页.
Okay.
This
Okay. Show me this. Show me this. Yeah. Tell me this. Go ahead.
On the left, the sensor-derived embeddings form 4 clusters with a Ziller-Hot score of 0.919. The clusters are visible, but the separation is not very strong, and the points are more spread out. On the right, the label-derived embeddings form 3 clusters with a higher Ziller-Hot score of
Silhouette. We did the last time, right? We said the last time. It's French. The pronunciation is silhouette. Go ahead.
Silhouette. Okay, silhouette score
Please
of
repeat every class, please. You guys learn learn some French, guys. Learn some French. Go ahead.
0.33. The 3 groups are more clearly separated, which suggests that the label-derived features provide a more distinct behavior grouping. This difference suggests that label-derived embedding cluster subject mainly based on activity statistics, while sensor-derived embeddings may contain more fine-grained signal-level information.
Who knows? So what is this UMAP? You told me that you will tell me what is the UMAP. So what is the UMAP?
UMAP is a projection. I think it's a.
You think? Okay, go ahead. Go ahead.
I just saw it as a way to project the data to make it more visible.
Is it linear or is it non-linear?
Okay, I don't know.
Okay, so again, if I were your boss, if I were your boss, what would
linear. I'm not sure.
No, I am sure. I know that I will fire you. Go ahead. Next slide.
Yeah.
Thank God I'm not your boss or your mom or your girlfriend. Go ahead.
This okay. For the sensor-derived clusters, the activity time fraction profiles are quite similar across clusters. The dynamic and static fractions are also close to each other. This means that the sensor-derived clusters are not mainly separated by activity composition or by overall dynamic static behavior. Therefore,
let me read the slide. So you have the clusters. And then you see, the dynamic fraction and the static fraction, okay? And what is the top one? Top one is the activity label. And then you see how much goes there. And you have 0. Let's see. Just a second. Cluster 1, 2, 3. So 0, 0, 2, 1. So you see that the issue is that the last 5 activities, they never happen, right? So they're nowhere, right? And the issue is that yeah, so you see that the biggest issue is that one there, right? That you just don't have points in the last 5 activities, right? That's what we said the last time, right? That those activities are very rare. So okay, go ahead. Tell me what is this dynamic fraction and this static fraction?
Therefore, the sensor-derived cluster may reflect more detailed sensor-level differences, such as how subject perform and the same activity, movement intensity, or signal variance.
But I ask you, can you explain to me the dynamic fraction and the static fraction? What is this? What is it?
Okay, sorry, I don't know. I recognize I spent very less time on this challenge. I'm sorry.
Go ahead. Next slide.
For the label-derived clusters, the profiles are easier to interpret because the embeddings are directly built from activity statistics. The dynamic static ratio shows clearly differences between
But what is
clusters.
the dynamic fraction? What is the dynamic fraction? How do you calculate it? What is the dynamic fraction? What's the formula?
I check my code.
Check your code. Otherwise, you're telling us something about the dynamic fraction. You don't know what it is. What are we supposed to do with this? I see this group is the group that is gonna make me. It's gonna cause me to lose the most hair, or to get the most white hair, guys. Gosh. I'm gonna remember you. Okay, you can just go ahead. Don't worry. You can just show me the next slide, and then you tell me later what is this. You go to the next task. You tell me.
Okay.
Let's see if you know what's on the next slide.
好，下一页吧。The main setting is treated as the reference setting, so its AI and NNI versus itself are both 1.0. When changing the polling method to global mean polling, AI drops to 0.2 and NNI drops to 0.34. When using activity mean plus standard deviation, ARI is also low at 0.17. This indicates that the polling method affects the resulting clusters. Changing the distance metric has an even stronger effect. When cosine distance is replaced by Euclidean distance, ARI drops to 0.04 and NNI drops to 0.11. This suggests that the cluster result is highly sensitive to the distance metric. Changing the algorithm from agglomerative clustering to k-means give ARI 0.44 and the NNI 0.56. This is still different from the main setting, but less severe than changing the distance metric. Overall, the clustering results are sensitive to polling method, distance metric, and clustering algorithm.
Okay.
Among these, the distance metric appears to have a strong effect. 好，下一页。This slide checks whether there are subjects that behave like outliers. Here, I use per subject silhouette scores.
Again, silhouette.
Okay. Scores. The x-axis is the silhouette score in the sensor-derived clustering, and the y-axis is the silhouette score in the label-derived clustering. A lower silhouette score means the subject is less well matched to its assigned cluster. If the score is below 0, the subject may be a boundary case or an outlier candidate. Most subjects have positive silhouette scores in both views, so there is no strong evidence of many outliers. Subject 13 has a negative sensor silhouette but a high label silhouette. This means
this is also, but this is true and not, right? Because we know that there are some activities that are only recorded like 3 times, right? That's what we saw last time with the other group, right? That they had these 5 clusters. 2 of the clusters they only contain 1 element. Right, so of course you don't find any outliers, but did you check how many elements you have per clusters? Because I suspect that 2 of the clusters only have 1 element, right? So I will call them outliers, right? Go ahead.
Okay.
I don't believe it. I don't believe what you're saying. Go ahead. 下一页.
Oh no, 还没. Okay, 30.
What do you want to tell me? Because we know that there are outliers, right? We know that there are outliers because the what is it, lay to stand and stand to lay, it happens only 2 times in the data set, right? So how is that not an outlier? Right?
Yes.
Okay, so let's go to the next task. Okay, let's see. Okay, next.
The challenge here is what we call online activity detection. Most activity recognition setup treat each window of sensor data as a single classification problem. They see a window, they predict an activity, but in a real-time system, the model is running continuously, and at every moment it has to decide, do I have enough evidence yet to declare what the user is doing, or should I stay silent? If the model commits too early, it's give false positive every time someone transitions between activities. If it commits too late, the system feel unresponsive. So we need a model that knows how to wait. Our approach is to give the model a blank class 0, in addition to the 12 activity classes, making 13 output classes total. We train the model on target sequences, where the first delta second after each activity onset are labeled blank. And only after that grace period do we start labeling with the actual activity the model learns to wait. The whole system has to be casual. At the time t, the model can only see frame up to t, never into the future. And as a comparison, we also train an offline bidirectional classifier that has access to the full window context, so we can measure exactly how much performance we lost by going casual. Next slide, please. Quick setup. We use UCI smartphone HAR dataset, 30 volunteer wearing a waist-mounted phone with a triaxial accelerometer and gyroscope sample at
Gyroscope. It was almost
gyroscope.
perfect. It was almost perfect, but really good, really good. I'm just joking. I'm just joking.
Okay.
Of course, I'm just joking.
Sample at 50 hertz that give us 6 channel of raw sensor data. The dataset has 12 label activity, 6 basic one, walking upstairs and downstairs, sitting, standing, and laying. And 6 postural transition like sit to stand and stand to sit. We split the 30 subject into 21 train, 2 validations, and 7 tests, with sit 42 exactly matching task 1 split, so all our results are directly comparable to the earlier work. We trained 2 models, both with a hidden size of 64. The online detector is single layer group, unidirectional, that's what enforce casualty, with a per frame head outputting 13 classes, about 14,700 parameters. The offline baseline is a single layer bidirectional LSTM with a window level head over 12 classes, no blank class, about 38,400 parameter. So it's roughly 2.6 times larger than the online model. Training was standard. Adam optimizer at 1E-3, batch size 64, 30 epoch, frame level across entropy with teacher forcing on the blank augmented target.
Yeah.
We verified the online model is genuinely casual with perturbation test, where we shift the input at future time step and confirm past output don't change. Max difference was 0.
Okay.
Next slide, please. The first is the delta ablation. We train the online group 4 times, once for each grace period of 0.25, 0.5, and 1 and 2 seconds. And the measure for thing, frame-wise F1, for declaration rates, mean detection delay, and how many of the 281 281 test segment demodel successfully detected.
Okay, give me a
Actually-
second. Give me a second. So the frame F1, the frame is 10 seconds. How long is the frame? So what is the
you-
frame? Yeah, the frame here, the frame, how long is the frame?
Let me see.
Be 120, 120, 128, something like that. False detection rate. So that complements the F1 score. And the delay, right? So the delta is the grace period. And then you have the delay. The delay here, you mean the... Okay.
The frame is 20 ms.
Okay, 20 ms. Okay. So here, what do you mean by delay here? You mean that the number of blanks before it declares, right? That's what you mean by delay, correct?
Let me look.
It should be seconds, right? This delay should be seconds, right?
Yes.
And it's the number of seconds by which you declare blanks, correct?
Delay is detection delay, you mean?
Yeah, it's a detection delay, right?
Yeah, it's how long it takes the model to commit the correct activity.
So this is average across. Yeah. If you have a plot of these delays by activity, it would be great.
Oh.
I hope you are not going to disappoint me in the next slide. I hope the next slide is going to be the delay per activity. And then the hit or miss. Okay. Yeah, because here the hit or miss. This is macro F1 score. Frame F1 score. That's a macro F1 score, right? Yeah, across all classes. Okay, good. Show me the next slide. It's nice.
Next slide.
Stay there. Let me parse. So here you fix your your grace to be 0.5. And then you compare the F1, FDR, the blank. So why is the BLSTM also declaring blanks? The BLSTM should not be declaring blanks, right? So this blank state for the BLSTM, it should just be 0, right? Hello?
Let me look.
You understand my question, right?
Can you rephrase it?
So the BLSTM, right? The BLSTM is also outputting zeros, right? But in the original data set, there is no label 0, right? There is no blank that the BLSTM should be outputting, right?
Oh yeah, it should be 0.
Okay. And then we compare, right, the performance, and that's the F1 score. So everything goes up, but walking, right? Of course, because here the F1's okay. Yeah, good, nice. Okay, go ahead.
So we compare our online group against a bidirectional LSTM baseline, same hidden size, same data, and same subject split, just bidirectional and window level instead of casual and frame level.
Yeah.
Expected the offline model to win because it see the full window context in both directions. But look at the top of the table, only online F1 is 0.6, offline is 0.36. Online wins by 0.24 points. The reason is the row right below for declaration. Offline is at 0.48. Nearly half its frame are mislabeled. Why? Look at the blank state percentage. Offline never predict blank. About 42% of our test frame have no label activity. They are the gap between segments. The online model correctly stays silent on those. The offline model has no choice but to guess. The per activity breakdown tells the same story two-way. On the steady state activity like walking, laying, standing, the two models are basically tied. But on the postural transition, online dominates. Stand to sit is 0.46 versus 0.1. Sit to stand is 0.5 0.59 versus 0.05. Offline simply can handle short transition because it has to commit to one of the 12 activity classes per window. So the takeaway here is that the blank class isn't a handicap. It's the whole reason the online detector outperforms a stronger model.
You're so poetic. You're so poetic. You should try to, yeah. You should work in finance. Go ahead.
Next slide, please. So wrapping up with the 4 questions from the spec. One, what's the optimal delta? The answer is 0.5 seconds. It maximizes F1, minimize detection delays, and catches the most segment. The trade-off curve has a clear knee right there. 2, does the online detector match the online classifier? It's bitted by 0.24 F1 points. The blank class compensates for losing future context and then some because offline has no way to handle no activity frame. 3, premature label and proactivity differences. 4, declaration rate is about 30%. Steady state activity like working and laying are easy. F1 between 0.65 and 0.87. Postural transitions are hard. F1 between 0.29 and 0.59 because they're often shorter than the delta grace period itself. That's why 49 out of 281 segments are mixes, almost all of them transition. 4, encoder choice, we only train the group. A TCN with a similar parameter count would probably hit similar steady state F1, but with slightly longer warm-up due to its respective field. We left that as future work. Overall takeaway, a casual group trained with a blank class is a practical, deployable recipe for online human activity recognition. The delta parameter gives you a knob to trade latency for reliability, and 0.5 second win the trade-off cleanly on the datasets.
Very good. Do you wear any wearables? Do you have any wearables yourself?
No.
Because you say future work, right? So I assumed you wanted to work on a startup for wearable technology. You know, if you want, I'm here to help you. You know, I'm always happy to help the students. Yeah.
Oh, I consider.
Okay, very good, very good. Okay, that's it.
And next task.
Next task. Let's see this one.
So I will now present text work, one-shot subject personalization. Our goal here is to see how we can make our model work well for a completely new user using only a very small amount of data. Next page. First, we'll look at method 1. First, we get a new data from a new user. Next, we extract k-shot samples. This means we only take a few samples, for instance, 1 or 5 samples per activity. Then we use these few samples to feed a standard scalar. We use it to adjust the user's data. Finally, we evaluate the baseline model. The most important thing here is we do not retain the model. We only adjust the input data.
Let me ask you something. Does the learning setting make sense to you? Do you appreciate the learning setting?
Half.
Let me ask you. Go back one. So usually this one. Go back one. So this one-shot personalization, right? So, for example, I'm sure that you already saw it, right? So, for example, when you have your voice assistant, let's say your Siri or your Google Assistant, voice assistant, right? You do understand that the assistant is personalized with your voice, correct?
Yes.
So how do they obtain this personalization? Is this type of stuff, right? They record you saying, "Hey Google," a certain amount of time. They extract a feature for your voice, and then they personalize the model based on your voice, right?
What about it?
See, and of course it works very well, right? So the application is actually very, very practical. You know, it's something that you do all the time. It's just that you're not, if you're not aware of it, you don't think about it. Does it make sense now?
Yes.
It's the least enthusiastic yes I've heard the whole day. Go ahead. Yes.
Next page. We'll see the result from method 1. Look at the red dashed line. That is the zero-shot baseline. It is very low, only around 0.1. And now we'll look at the blue line, which is the method 1. As you can see, with just one sample, which k equals to 1, the score jumps to 0.64. This is a huge improvement, and the score stays above 6 as we add more samples. Next page. And what's our finding from method 1? First, the general model fails on new users. Why? Because everyone puts their phone in different places or works differently. We call this subject level bias. And second, we find method 1 is efficient. We call it one-shot recovery, and it works simply by input space alignment, making the new user's data match the model's training data. And so how many samples are required? Our answer is maybe just one sample is enough to fix the failing model. However, small samples can have high variance. To get a more stable and reliable result, 5 to 10 samples are recommended. Next page.
Okay, so in the challenge, we study smartphone activity recognition using sequential neural networks. The goal of Task 4 was to adapt the model to unseen subjects using only a few calibration samples. We use a GRU-based model and compare 3 personalization methods under different K-shot settings. And
Okay.
next slide, please. So we compare 3 personalization methods. The first method was subject-specific normalization, which recalculate the sensor mean and standard deviation using calibration data. And it was just mentioned the slide before. And the second method was the prototype classifier. We extracted GRU embeddings and classified samples using the nearest prototype. The third method was linear head adaptation, where we froze the GRU encoder and fine-tune only the final classifier layer. And next slide, please. So these figures shows the macro F1 performance under different K-shot settings. The dashed line represents the zero-shot baseline. Among the 3 methods, subject-specific normalization achieved the best overall performance. Prototype classifier and linear head adaptation both significantly outperform the zero-shot baseline, and prototype classification worked especially well in the low-shot settings. And next slide, please. We also analyze class-wise recall.
Okay.
Static
Let me pass.
activities.
Wait. Zero-shot recall, one-shot recall, 5-shot, 10-shot recall. Yeah, you see here what I was saying before, right? That what I was telling you before, right? That the sit to lie and the lie to stand, and also the sit to stand, like all these activities, these are transitional activities. There are very, very few samples, right? So you see that of course, walking is the most frequent one. Sitting and standing is the most frequent one, but you see that like the number of samples per activity is very low in this last 5, right? And also you see that we saw the clustering images before. Basically, it was never assigned there, right? So my suspicion here is that yeah, some of the classes they just have no samples, so it's very difficult to learn. Okay, go ahead.
Okay, so static activities such as standing and sitting achieve high recall scores. However, transition activities such as sit to stand and lie to stand were much more difficult. This suggested that the dataset is highly imbalanced and that transition activities are harder to model because they are shorter and more variable.
Exactly.
And during implementation, we encounter several problems such as missing models after runtime reset and unstable linear head adaptation. We solve these issues by retraining the baseline model, adjusting hyperparameters, and reducing the batch size. In conclusion, personalization improves unseen subject performance, and subject-specific normalization achieve the best overall result. And next slide, please. Thank you very much.
Thank you very much. Did you expect this slide? Because it seems like you didn't expect this slide, right? You were surprised by this slide. Do you have any wearables? Do you wear any wearables? Tell me. The last speakers? The last speaker, do you have any wearable? Yeah.
Wearable.
Yeah, do you have any wearable?
Like watches.
You have watches? You have a digital watch?
No, not digital.
So you have an analog watch?
Yes.
So I don't want then I think it doesn't classify as a wearable. Which analog watch do you wear?
Normal one.
Is it a Casio? Is it what is it? Can you tell us what type of watch is it?
I think it just bought in the night market or something.
Oh, I see. So it's a Taiwanese brand. So it's nothing fancy.
I don't even know what brand it is, actually.
But you're sure it's not a Rolex, right? It's not written Rolex on top.
It's not that.
It's not a Rolex. Okay. Is it Audemars Piguet? Maybe no. What's written?
I do wear Casio before.
You had a Casio before, like the big one, the rough watches.
No, digital one.
Okay, very good. Yeah, because so if you look at the statistics, right, the Apple Watch is the most common wearable, right? I think it surpassed all of the watch brand together, like also the analog watch, right? I think the Apple Watch is the most watch wearable, the most worn wearable ever.
Oh, yes.
Yes. Okay, very good. Group, let's do a little break. We walk around a little bit. 3 minutes to get some more and walk around, and then we do with Group E, okay? So Group E, get ready, please. Let's have a 3 minutes break. Okay, guys, very well. Can we listen to group E, please?
Okay, we are going to present challenge 3.
Okay.
Okay, this slide shows the overall workflow of our implementation. First, the program downloads and loads the UCI HAB dataset. Then the raw accelerometer and gyroscope signals are combined into 6-channel time series data. After that, we split the data by subject to avoid like data leakage, apply window segmentation, and normalize the sensor channels using only the training data. Finally, we train the baseline model and run the experiments for different tasks. And the results are saved as tables and graphs for later analysis. So this slide shows how we train the baseline GRU model. We use like the run baseline experiment function to train the model with prepared raw data, subject level splits, and default configurations. And the graph shows the training and evaluation results of the baseline GRU model. From the training curves, we can see that the training loss and validation loss both decrease quickly in the first few epochs. After that, the curves become more stable when it's around like 10 epoch, which means that the model has learned the main patterns from the sensor signals. And for the accuracy, both training and validation accuracy increase and stay at a high level. The training and validation curves are also close to each other, so there are no serious overfitting in the baseline experiment. However, the macro F1 score is lower than the accuracy, which means that although the model performed well, some classes are like still harder to classify correctly. This is the confusion matrix, which gives a clearer view of this problem, like from basic activities such as like walking upstairs, walking downstairs, lying. Like the model performs quite well because most value are on the diagonal. But for the other cases, such as like sit to stand, stand to sit, the model makes more mistakes. But it's reasonable because like the transition activities are more similar to each other, so they are harder for the GRU to distinguish. And
Wait a second,
overall, the yeah.
Let me pass a second. Sitting and standing, right? So because okay, sitting and standing are very confusable, and then sit to lie and lie to sit, sit to lie and lie to sit, and stand to lie and lie to sit. Sit, what? Stand to lie to stand. Wait, what? Just a second. So, oh, okay. Stand to lie to sit. Okay.
So like
So it comes. So basically,
complex
how you
one.
go ahead. You were saying?
Okay. So like the complex one are less likely to be distinguished, so it's not.
No, I was thinking the following. You see that sitting and standing, they get confused easily, right?
Yes.
So I was wondering if for example, if the lie to sit and the lie to stand, they're also confused easily. And then I got confused in my own
Like-
brain. I was looking at.
Oh,
You understand what I mean, right? So standing
yeah.
and sitting are easily confused. So I was checking if sitting and standing to lie, they're also easily confused, but that's not the case, right?
Yes.
You just confuse lie to sit and lie to stand. So that's correct. And then you confuse sit to lie and stand to lie. Okay. So it makes sense. Okay, good. So it makes sense. Okay, it makes sense. Also, the transition confusion is the same as the static confusion. Okay, go ahead.
Okay, so for the baseline Jaru model can recognize more basic activities well, like I would just say like walking, sitting, and like lying. And for the transition activities remains the main challenge for later experiments. So for task 1, this slide shows the code for window length experiment. Here we used run window length experiments function to train and evaluate the model with different window sizes. The purpose of this experiment is to check whether giving the model more past sensor data can improve recognition performance. At the same time, I also want to observe the trade-off because a longer window means like a higher latency as usual.
Also more complexity, right? Because if you have more.
Yes.
Okay, go ahead.
So this figure we can get from the code, which shows that the validation performance under different window lengths. From the accuracy curve, we can see that the accuracy stayed quite stable for most window sizes. So increasing the window length does not bring a very large improvement in accuracy. However, the macro F1 score shows a difference. The macro F1 is better around like shorter windows, especially around 1 second. But it gradually decreases when the window becomes too long, which means that the longer window is not always better, though it provides more context, but it also increases the latency and like the complexity and unnecessary information. And this slide shows the code for the prediction horizon experiment.
Horizon.
Here we use horizon, sorry.
Think
Here we
about
use
the Nolan movie, right? Yeah. Or Event Horizon. Yeah. Anyway, go ahead.
We use run horizon experiments function to test different prediction horizons. The prediction horizon means that the model observes the current window, but it needs to predict the activity at a future time. This experiment helped us understand how far into future the model can still make reliable predictions. When the prediction horizon is 0 second, the model only needs to recognize the current activity, so the performance should be and is the best. As the horizon increases, the model must predict further into future and the task becomes like more difficult. So the accuracy and the validation should drop. From the figure, the accuracy only drops slightly, but the macro F1 drops much more clearer after 1 second.
Yeah, of course.
Or
of course.
0.5. It drops very big.
Yeah.
This means that the model can still predict many common cases, but it becomes worse on some harder or less frequency classes like standard sits to light, something like that. So overall, the future prediction is harder than current activity recognition, especially when the horizon becomes longer. This slide shows the missing data experiment. In this part, we simulate different types of degraded sensor data, such as random point dropout, block dropout, channel dropout. And the goal is to test how robust the model is when the input signal is incomplete. And you can see from the results, dropping the accelerometer channel has the largest negative effect, which means
course.
that
Yeah, go ahead. Finish the sentence. Yeah.
okay. So which means that the accelerometer signals are very important for recognizing human activities.
So question. So the accelerometer has 3 channels, right?
Yes.
Okay. And here you drop all of the channels together, right?
Yes.
Because because I think that's the story, right? So if you drop, for example, the Y or the X, yeah. Anyway, so the Z should be the one that has the most information. And then notice that here, right, is the results are average, right? Or because look at how the block L10 has a higher F1 score than the non, right? That's correct, right?
Yes. Yes.
I wonder why the performance improves.
You mean improves?
Yeah, because the non is in the middle, right? Non is there. Non is there. Non is
Yes, here.
right?
Oh, so you mean like why
Yeah,
none is here and
yeah, exactly. Because the results are average, right? Over what, like 10 seats or something, right? So it's not probably it's within the error variance, whatever, the error boundary. But it's strange, right?
let me think. Why will it increase? I think that like the block L, this one,
Yeah.
removes like only very short continuous segments. So the lost information is limited, but like
0.5, it's larger, right? I mean, 0.05,
yes.
it's kind of large, right? So
I think it's more like a experiment.
yeah, next, you know what? Next
How
time,
do I
put the
say it?
error bars. Put the error bars next time, and we will see from the error bars if the issue is
Yeah.
the variance. Yeah.
I think that will make the graph more like reasonable
Yeah. So
because
we
the
understand.
non is like here.
Exactly. Okay, very good.
Which so dropping the gyroscope also hurts here the
Gyroscope.
performance, but it's gyroscope, sorry. But it's
Don't say
not
sorry.
as serious.
Don't say sorry. Go ahead.
But it's not as serious as dropping the accelerometer.
Of course.
Yeah, for random points dropout and small blocks dropouts, the performance is closer to the normal setting, so the model can still handle some local missing values. So
Mhm.
overall, the channel dropout is like most harmful than random missing points because like losing an entire sensor removes the whole type of motion information and just kills the validation.
Of course.
So here we compare different model and architecture. We compare the logistic regression, CNN, GRU, and STM under 2 window lengths, which are 1 second and 2.56 seconds. From the result, logistic regression has the lowest performance because like it is simpler model and can capture temporal patterns very well. And CNN and GRU perform better, which shows that the sequence and local temporal features are useful for this test. CNN gives the best or very close to the best performance in this experiment. LSTM does not clearly outperform the other models here, which shows that a more complex recurrent model is not always the better. And overall, the model choice should consider both performance and cost. So for
this task CNN and GRU gives a better trade-off than the simpler logistic model or the LSTM. Next.
Okay, is text 2 and next slide.
Next slide, please. Next slide, please. Don't sleep on the slides.
Okay. To ensure experimental rigor, and we applied standard scaling and dynamically found the optimal cluster count for k equals 2. And we evaluating the consistency between these two methods. Our ARI is 0.066 and NMI is 0.097. And it proved a clear semantic gap, and it means that a person's macro-level physical movements that cannot directly predict their macro-level lifestyle. And next slide. Okay, and the clustering here is based on physical, kinematics, and movements in
Kinematics.
Okay, sorry. And for
Don't say sorry.
instance,
If I say something about the pronunciation, it's just to be clearer, okay? It's not what I'm here to teach you. Go ahead.
okay, thank you. And for instance, cluster 0 and cluster 1 are clearly separated along component 1. And these suggest that the model has identified two distinct styles of movement within our cohort. And perhaps based on the force of impact or the speed of gait.
Okay. Just explain the label to me. Explain the label to me, right? So you have cluster 01 and source sensor. What is the meaning of that? Yeah. Explain to me. Explain to me.
Oh, the source and the sensor didn't appear on the plot.
But because they are not here, right? Probably because they're not here. Okay.
Okay. Should I go through?
Yeah, go ahead. Go ahead. I mean, if that's not here.
Next
I
slide.
understand it's two clusters, yeah.
And next is the label derived PCA, in which clusters subjects purely by macro level behavior routines. The key finding here answers the test question about outliers. And we can look at the far right. Subject 28 is isolated in its orange cluster. Since we avoid demographic claims, this indicates an extreme behavior profile, such as remaining almost entirely static with zero activity transitions. This proves that label-derived features are highly sensitive to extreme lifestyle anomalies.
Yeah.
Yes.
Let me think. So here the clustering is k-means, right? You did k-means for the clustering?
Yes, the k-means is 2.
And you have multiple restarts, right, of the k-means? So because it's but from the PCA it's clear, right? But did you try more clusters or not? Because I think
we let the algorithms to choose the k, and its output is 2. So I
mean, you can also plot the elbow. You can also do the explain variance plot, right, and see what is the explain variance.
Oh, okay.
Yeah, because here it seems that the first two PCA components don't help you much, right? So maybe you have to try some other clustering approach. Okay, go ahead.
Okay, and next slide. And we can look at question 1 first. And physical movement features cannot directly infer macroscopic daily routines. There is a massive semantic gap between the two. And for question 2, and two distinct logics emerge. Label-derived clusters group the subjects by macro-level activity proportions and transition behaviors, reflecting their lifestyles. In contrast, sensor-derived clusters group them purely by micro-level movement, intensity, and kinematics. In question 3, even if the clustering algorithms changes and the ARI, MNI scores remain extremely low, the core conclusion of the consistency doesn't change. And for question 4, this isolation is caused by extreme behavior data and not by demographic difference like age or gender.
Correct, right.
Okay, and we can go to text 3.
Are we going to the 3? Maybe not.
Hello.
Hello?
Okay.
Do you want to talk to us?
I can start.
Yeah, of course.
The core objective of this text is to transition from an offline classifier to a casual real-time system that predicts activity sequentially from continuous sensor system strings. To handle uncertainty and motion transitions during activity change, we implement a special brand class designated as class 0. To ensure real-world feasibility, we enforce strict causality constraints, prohibiting any future data leakage in our model architecture. Ultimately, our goal is to explore and balance the key design trade-offs between detection latency and classification accuracy. Next slide. Moving on to our first metric. This slide shows the distribution of online detection delays across all testing segments. This measures the time elapsed from the actual activity onset to the model's very first correct label prediction. As you can see from the histogram, we achieved an immediate response for the vast majority of activities, with over 250 instances successfully detected within 1 second.
Yeah, this is the plot that I wanted to see from the other group as well. Finally, I can see the plot. Huh? Go ahead.
And there is a moderate delay group between 1 to 2 seconds and a very thin long tail extending past 4 seconds for a few ambiguous activities. The takeaway headline here is clear. Over 80% of activity are successfully detected within 1 second, demonstrating higher responsiveness with a well-optimized brand class threshold. But how does the length of the brand period affect our error rate? Let's check the next slide.
I wanted to see the delay per activity. I want to see which activity has the longest delay. But go ahead. Go ahead.
Okay. Next slide. This brings us to the false declaration rate, which measures the percentage of frames where the model outputs an incorrect activity label instead of staying silent with a blank token. We experiment with 3 different grace periods, delta. At a short grace period of 0.25 seconds, the false declaration rate is high, at around 43%, because the model is forced to make a guess too early. However, we increase delta to 0.5 seconds. The false declaration rate drops significantly to its lowest point at 80%. Interesting. Further increasing delta to 1 second causes a slight error rebound back up to 21%. Therefore, we can conclude that a 0.5 second grace period provides the optimal trade-off, reducing false declaration to 80% by giving a casual encoder sufficient time to resolve signal ambiguity. Let's summarize the engineering insights behind this phenomenon. Next page.
Okay.
First, the 0.5 second grace period acts as our architectural sweet spot, effectively clearing out overlapping signal noise. In contrast, the 0.25 second setting creates urgency where the network is pressured to predict prematurely, spiking errors to 43%. The 1 second setting over penalizes the network during training, distorting decision boundary and causing a 21% error rebound.
Yeah.
Second, regarding the long tail delays, these are caused by high similarity dynamic movements, like walking versus walking upstep, or slow postural transitions, which require the casual model to sustain a bank state longer to ensure confidence. In conclusion, while offline models achieve higher raw accuracy by looking ahead, our online casual model balance a minor 0.5 second delay to deliver real-world deployability without catastrophe false alert. Okay. Next slide.
Okay, so for the task 4, the goal of this task is essentially like to test whether the our activity recognition models like improves when we adapt to new subjects. Next slide, please. So the different models we use like methods are the zero shot, the subject-specific normalization, the prototype classifier, and the linear allocation. And kind of like looking at the graph, you can see that prototype, like in the end after the 10th K, is performing the best. But if we go to the next slide, please. Yeah, we can see like this is I didn't actually like print out for all of the different activities. So here, but we can see that it cannot, like for the zero shot at least, or K equals 0, it cannot like predict the like stand to sit to stand, sit to lie, like to sit and stuff like that. It has a really hard time doing that. And if we go back one slide.
Yeah, go back a second. Yeah. No, back.
Yeah.
Okay.
We
here,
can see like
just stay there a second. Yeah, go ahead. Tell me. Yeah.
Yeah, the macro F1 kind of increases, but like based on these observations, we can assume that maybe it doesn't predict really like the harder to predict what we call like activities. We just kind of like gets better at the ones that are easier to predict. But we can also see like at the what do you call like K1, like it kind of drops in performance for a lot of the things. And for the linear one, we can see like we can barely see it. It's like you don't even see the blue, right? Because it's pretty much like right on top of the zero shot. And looking at the graph, like on the left, you can see that like it's I think it's like it's slightly better by like what is it 0.0005. So you can't even see it.
So of course, performance is not good.
Yeah, exactly. And then going to the questions to answer, so 2 slides. Next slide again. Next slide again. So here, so based on these things, we can see that
copy and paste from Gemini. Go ahead, guys. Jesus, I mean, you can be lazy, but not that lazy to just copy and paste. Jesus, I understand. It's the semester, you don't want to do a lot of work, but come on, don't make me read this wall of text. Go ahead. Give me a nice summary. Give me a nice summary. Go ahead.
Yeah. Essentially, the performance gap between the global model and the zero shot performance is essentially like it's like the personalization doesn't really close this gap that much. It just like mainly like I think the difference is like 0.02 in accuracy between the two. So even with the personalization, like it doesn't really close the gap that much, I would say. And then for the which personalization performs it best for one shot or a few shot calibration, and if it's consistent across subject and activities. So for one shot, actually the linear head adaptation is the safest option because I think it only like changes in the last layer of the classifier. So it's quite similar to zero shot, right? So it's not that different. While I think for the prototype at the other normalization wing, it drops in performance for the first one. And then how many calibration examples are required to achieve a given accuracy threshold? Like I think for the most of them, it's like around 5, K equals 5, where like it kind of doesn't drop and like keeps increasing, and then that kind of reaches the point where the accuracy is the best. And then the subjects profile vectors from task 2, I didn't do them because it took a long time to run. So
Are you giving me excuses? Are you giving me excuses?
maybe.
Your mic is very trippy. I think it's you bang the mic somewhere. It gives you a very electronic voice. It's kind of.
I'm using my laptop mic. I could try to use my headphone mic, but then like my sound quality becomes really weird because I think the headphones, but they have both like input and output, it kind of like performs worse in the input.
It's just very trippy. Yeah, it's audible. It's just very trippy. There is some artifact. Okay, very good.
Right, then that's it.
Oh, that's it. So you leave me with a ChatGPT slop of text. You don't not even a thank you slide. Oh my God!
Sorry.
You really don't care for me. Okay, very good, guys. Tell me what you want to do, right? So I'll give you 3 options, right? What do you want to do? 0. Stop here. 1. Review challenge 4. 2. Do some class on auto encoding. Tell me in chat what you want to do. We have a movie review. We have a movie review, guys. Then we do the movie review. Forget about the rest. Let's do the movie review, guys. Thank you. Let's do the movie review.
Okay, let's see if I can switch the mic to my headphones.
Yeah, exactly. So you don't have to hear. You sound like a Megatron, you know. You sound like a 1980s supervillain.
Oh, can you hear me?
Keep talking.
Hello. I don't know if it's delayed or not.
Okay.
Is this a lot better?
I think it's still not sure the quality, but we'll deal with it. Okay, go ahead with the movie review.
Okay.
Take as long as you want. If you want to take 3 hours, 4 hours, go ahead. We are all here listening for you.
Oh, I don't know if I can do it for that long, but let's see.
Wow, I like this movie. Okay, go ahead.
Yes, so the movie I decided to review or like watch is Train to Busan because I've heard like a lot of things about.
Go to presentation mode, please. Go to presentation mode. Yeah.
Oh yeah, right. Sorry.
Go ahead.
Yeah.
Let's see in
Why
chat
is
how
this
many.
free?
So let's see in chat how many saw this movie. Did you see this movie? 0/1. So that you have to tell people if there are spoilers, right? Otherwise, you're not a good YouTuber, you know.
I tried to keep it like not as I tried to exclude a lot of the spoilers because it's like I think I spoil like a little bit in the beginning, but it's like you see it in the trailer anyways, it doesn't matter in my opinion.
Very good. Let's see. Okay. Seems people have seen it. Okay, go ahead.
Okay. So introduction. Essentially like so the director, I don't know like if this is important, but like I think the release year and the genres are probably important. So it was released in 2016 and it's an action horror ensemble movie and the ratings here are, I don't know like what is a high IMDb rating? I think this is okay, right?
I think
like the ratings are
on general, the rating of the horror general, they don't go above 7.5, 7.6. Yeah, I don't think it reaches an 8.
so I think this movie probably like pretty good in this genre. So essentially the plot in summary is just like really brief. So it's basically a father and daughter. They are taking a train to visit like I think the daughter wants to live with their mother or something. So they take the train to Busan. And then like when they enter the train, like everything around them starts to become chaotic. They see in the TV, like, oh, people are protesting and stuff like that. And then they're just like chilling in the train, and meanwhile they're in the train, they kind of realize like the world is turning into chaos, and also in the train, of course. And this like all of them try to stay alive and like kind of do their thing, you know. So the characters, I'm only presenting the characters that I think are relevant because like there are like so many characters, you know. So this is the father. So in the beginning, you kind of realize he's a terrible father. He's, I think he's a what do you call it, fund manager in Korea or something. Yeah, where like so you kind of see that he's a terrible father because he barely knows. I think it's like his daughter's birthday. He barely knows what she likes. He's like, oh, so what do kids even like nowadays? And then he buys a gift, and it's the same gift that he gave to the daughter like a year ago. So imagine like you're the kid, and then your dad gives you like the same present 2 years in a row. Or like, yeah, that's. I was like, oh my god, when I saw that. And but then he's also like really selfish because he doesn't really care about like I think like as a fund manager he prioritizes himself a lot. And like for small companies, like as fund manager you like kind of handle other people's money, and he doesn't really care about like the small companies and stuff like that. He just like drops I think all of the funds and stuff. And then we also know that he has like some marital issues because I think they're like going through a divorce with his wife. I think they mentioned it. And honestly, I think it's probably that he's like really selfish and busy with work that he kind of can't really spend time on other things. And then we have the other characters that are important. So the daughter. So in this series, you can kind of see that she's like really emotional and morally aware, even more than like a lot of the like adults, because she's like still considering like a lot of the moral things that humans usually consider. But obviously, in like a zombie apocalypse, a lot of people kind of don't really care about this. And then we have the Sangwa, which is the one in the middle here, and he's like really courageous. And I wrote like, oh, big strong guy, because he's like the one that is like fighting the zombies, and he's like really strong and stuff. And then his pregnant wife, who's like really caring and takes care of Suan actually a lot. And she's also really brave and stuff, despite like being pregnant and you're like really vulnerable, right? But she still like kind of has this really brave upfront, what do you call it? Yeah. So in the movie, they have a lot of suspense. Like in the start of the movie, I think maybe the first 20 minutes or so, they have no background music. And for this, like in like what do you call it, the cinematic things, usually like I think it's like it's really uncomfortable for us to have like no background music at all, because like usually like even all of the sounds and stuff you see in movies, stuff like that, they usually have like some like almost everything is abstract, right? So when you do not have that, it's like it's really weird. But here is like so in the beginning they have a lot of things that hint that there is kind of zombie apocalypse coming up, and this is like one of the scenes I will show you. So here a deer gets hit, and then yeah.
Jesus.
Like after the scene, it just pans into like into like a normal kind of scene, and you're like, oh, like something is going to happen. So you always have this like anticipation of something really bad happening, but you don't really know what is going to happen. Yeah. And so the main themes of this movie is essentially like selfishness or sacrifice. So it's like so in the series you see kind of like a lot of characters. Some are like really annoying people that you really hate, that like are really selfish and like gets everyone killed because they only care for themselves. And then there's like the ones that sacrifice and get really sad when they die and stuff like that. And there's also like social criticism here, which like in society, like how society kind of handles these situations and stuff like that. Because I think in this movie, like the government doesn't really mention anything about like zombie apocalypse or anything. They just say like, oh, people are protesting and it's chaotic, So the people do not actually know what is happening. And also like family relationships. So you can kind of see like the main character and his daughter, like kind of their relationship, and also like how he grows as a person because of like this incident and stuff. And yeah, I think that is like really, really nice, because he goes from like really selfish to actually like caring about other people, which you see like several times in the movie. Yeah, and as I said, like how humans treat each other like during a zombie apocalypse. You can like I think that aspect is really cool as well. Yeah, so the cinema photography and atmosphere. This is like the thing I also talked about earlier. like the tension that you get like in the beginning. There's just a lot of tension. You know, you see the news. There's like, oh, something is going on, you know, and a lot of foreshadowing. Like so like news about the demonstration and like articles. I think even in the first scenes. Where it's like you see articles about like strange things happening to like wildlife and stuff. And you're like, okay, something is really odd here. Yes, and the personal evaluation here. So I would give it like a 7.8 out of 10 because like I think there are a lot of good things with this movie, but there's also a lot of bad things that trigger me a lot. So like I think the suspense and tension in the beginning was really good, and the camera work is like sometimes when they pan the camera to like different scenes, it's so well done in my opinion. And then like the character development of mainly the main character, I would say, is really interesting to see. But yeah, and it was actually really nerve-wracking because I felt like at some point of the movie when all of the zombies and stuff were running in and they got chased, like I felt my heart like beating really fast. And then I feel like this movie has like it has emotions but not enough because I really like really emotional movies where you really cry or feel a lot, because I feel like this movie it focused a lot of like the suspension and stuff, but the emotional stuff it's I don't know, I didn't really connect. Maybe it's me problem, but and then the zombies are like really fast, and I can show you like here in the scene. It's actually really fun. Yeah, so like I think usually in like zombie movies, the zombies are not moving this fast. So it was actually really funny. Like these zombies are flying all over like the different scenes and stuff. I'm like, holy shit! I've never seen zombies this agile. And then some negatives is that like a lot of the characters are really dumb. You know, they see a zombie like in front of them, and they're like, "Oh, what is that?" You know, and they're like, "What?" So it's like, yeah, and I don't know. There's so many decisions that they make that I'm like, why are you doing this? Oh, couldn't you have done something else? You know, there's so many ways to approach this situation, but they chose like the worst one, and I'm like, why? And then the zombie logic doesn't make sense. I think it's a lot of plot armor here, actually. So I'm like, you know, they will definitely die here. And I'm like, how did you not die? And like the zombies are so dumb sometimes for no reason. Like they're so smart sometimes and so agile. And then sometimes they're like the dumbest thing you've ever seen in your entire life. And then I feel like a lot of the things are really repetitive. It's always like, you know, the tension build up. And then like it kind of fades, and then like the same thing all over again, like for like 2 hours. I think that was kind of boring, and that's why I give it like a score of 7.8. I would say in general, I enjoy this movie, so it's not like a bad thing. But it's just like there are a lot of things that could be improved upon, but I still enjoyed it. Yes. Oh shit, whoops. Yes. So would I recommend it? Yes. I feel like it is. I would recommend you to watch it if you haven't, because it's like I think it's a nice movie to watch. It's not the best. I mean, it's like it's not the first priority. You know, if you have other movies that you think are good and you have heard better things about, I would watch them first. But this is like, oh, if you don't really know what to watch, maybe a zombie movie, it could be nice to watch. And also like a lot of the other like Korean series have referenced this movie. So I feel like if you kind of, so I feel like if you watch this movie, then you can kind of get the references a lot more, because I think this series probably or this movie is quite popular.
Like the series, yeah. I don't know. So Korean TV series, you mean? I'm not. Yeah.
Yeah, I think so, because I think I have watched like sometimes in the TVs of like the other series I've seen, like they mention Train to Busan, or they just like make jokes about Train to Busan, but I hadn't watched Train to Busan yet, so I was like, what is going on? You know, I felt like I was missing a piece of the puzzle.
Out of the loop subreddit, I understand.
Yeah. That's it. Like I haven't really done any movie reviews before, so I don't really know if I covered all of the things that are important for a movie. But thank you for listening, and that is my movie review.
Nice. Yeah. Any comment, guys? Any comments?
Any questions or comments?
Yeah, so the actor there, is the actor that was also in Squid Game, right? Is the guy, the father was also in Squid Game, right? I was just checking, right? This guy is
I think
in Squid Game. Yeah,
he's the one that dragged the main character into the game. I think
exactly.
it's good game.
Exactly.
Yeah.
And then yeah, because I remember this movie from back in the days, and it was one of the first Korean movies that I was aware of, right? Because of course the Korean movie industry has been receiving a lot of recognition internationally only in the last, let's say, 10 years, right? So when I saw it, it was more of a, I mean, when I heard of it, it was more of an underground type of movie. And then
nowadays, sorry.
Go ahead.
I think nowadays, like Netflix has a lot of like what do you call it, collaboration with like Korea, so that like there are a lot of shows and movies that are like Korean nowadays.
I think this is the biggest story of the last 10 years, right? The rise of Korean cinema, right? When they got the Oscar with Parasite, Squid Game was a big success. So I think it's the Korean media presence has been increasing a lot. What was I thinking? So because like if you look at the history of zombies, right? Zombies were seen often as a metaphor of like what will happen after the war, right? The invasion, the enemy. So yeah, so when you were doing the presentation, I was thinking about that, right? Because of course, I think there is something about maybe the political situation in Korea, right? Maybe what will happen, let's say if the war broke out, right? If there was a nuclear attack, right? I was thinking about the political situation in Korea, or if it's a commentary about how people will react to a disruption of the life that they have.
You mean like how people react to like a chaotic situation?
Well, North Korea drops a bomb, right? I think that's a type of commentary that is there, right? So, what would happen if the war broke out, right? If there was a nuclear bomb? That's just what I was thinking. Okay, very good. Any other comment, guys? Any other comments? Very good. And then I was thinking, the scene that you show me remind me of World War Z, right? Or even there, they are the super fast zombie, and also like the 28 days later, 28 years later, 28 weeks later movie series. They also have very similar zombies. Yeah. So that's it. Okay, very good, guys. You have to watch the 28 days later. Okay, thank you. Let's give him a clapping hand as a reaction. Okay, very good. I'll repeat the question to you guys. Tell me what you want to do. Otherwise we move on with our life. We do something else. I'm not sure when you guys are gonna start having the first. Okay, we can do one. Okay, so let's go to challenge 4. Let's go to challenge 4. If you want to drop off, of course, feel free to drop off. I don't know when you guys have your final exams, or if you have to study for your final exam. Go ahead. Again, sorry that I haven't posted the final challenge yet. I'll try to do it before the end of the week for sure. So now let's discuss challenge 4, because challenge 4 is very cute. It is very, very cute. It is very, very cute. Okay, good. So let me just close. What do? I go PDF here, right? So I do view PDF. Okay, boink. Okay, so the big story, one of the enabling technology. One of the enabling technologies of LLMs for sure are these word embeddings. Okay, let me correct it. Let me correct the word embeddings, because it's the spelling is important. Okay, so one of these enabling technology of LLM is clearly word embeddings. And word embeddings, when they were invented, they really unlocked our ability to work with NLP, right? Natural language processing. So the issue is that if you take language, right? Language is represented using, using GRUs and whatever. Language is represented using maybe bag of words and is represented using English fonts, but this is not a way of representing language which is amenable to processing by computers. Okay, so in order for computers to process semantic information efficiently, it seems that the key is to translate semantics into a vector space. Okay, so what this BERT does, right? It's a bidirectional autoencoder representation and a transformer. So basically, given a sentence, what it does, it transforms this sentence into a vector. Okay, and this vector, this is a pre-trained embedding, right? And this vector embedding is produced in such a way as to embed semantic geometry in the embedding space. Okay, so let me just show you here a little bit. Look for BERT. I'm expecting a couple of examples. Let's see if yeah. So this is I just want to have embedding. Let's see if they have. I just want to have a nice image to show you guys how BERT works. Okay, so not just technical plotting. Sorry guys. Here. This is the one that I wanted to show you. Okay, this is the things that you have to remember. Here, something like this. Share this down. Okay, good. So you can imagine that in the vector space, right? You want to have a representation like this, right? So if you take the word cat, right? What you can do is that you can look for the you can convert this to into a vector, okay, of a certain dimension, 700 something. And if you put the word cat into BERT, then it will spit out this 700 dimensional vector, okay? And then what you can do is that you can look at the words, the distance, okay, the distance between other words and the word cat in the embedding space, right? So here is showing you the cat, and it's telling you what is the distance in the vector space from other words, right? So cat is a living being, cat is a feline, and it's not close to human, it's not too close to gender, it's very far away from royalty, from verb, from plural, right? And then if you take kitten, it has this other representation. If you take dog, this is this other representation. If you take houses, take this other representation. Okay, so what you can do is that you can do PCA, and you can see in PCA the cat and kitten, they are very close in this embedding space. Okay, and you can see that dog is close to cat, but it's far away from houses. Okay, so it's clear that you want to use this vector space in order to represent topological meanings. And it's a little bit surprising for us that you can really represent, let's say, all parts of a sentence, all parts of a language in this embedding. And we don't have to sort of engineer this, we don't have to engineer any particular grammatical rule. We don't have to engineer plurals and singulars and declination and misspellings, right? But the embedding just take whatever language utterance you have, it puts in the vector space, and this operation is done in a way that preserves the semantic meaning for whatever it has been encoded into the embedding. So the best example that people use to show what is the effect, what is the semantic, what is the role of embedding semantic in geometry is something like this, right? So they take man, woman, king, and queen, and they take the embedding in BERT of this, and they show that if you take the distance between man and woman, the vector, right, that represents this distance is comparable as a vector to the vector between queen and king. So you can do some semantic operation in BERT, which are something of the following. You take king, you subtract man from king, and you add woman, and the result of this geometrical operation is queen, okay, which is semantically meaningful, right? But because what is a queen if not you take a king, you subtract the man, and you add in the woman, right? So it's intuitively this is the type of embedding this is the type of embedding of semantic into a vector space that you want to be able to do. Okay, so it's very surprising that this is actually, a perfectly meaningful operation, but it turned out that some smart people came up with this. Okay, so the point is that this model is very complex and it needs to be trained over many English utterances. So people do not train this model from scratch usually, right? But what you do is that you download the pre-trained model, and then you use this pre-trained model in whatever application you have. Okay, so you don't have to worry about spending a lot of training time into finding some good embeddings. What you do is actually just use the pre-trained model, which has been offered for us for free online, thanks to the goodness of the heart of some researchers at Stanford and many other places. And we're going to just go use it for this. Okay, so here you have a little bit the description of the architecture of BERT, and here are the NLP tasks that it's usually used for. And what we're going to use it for, we're going to use it for sentiment analysis. Okay, so since we were discussing about IMDb movies like 10 minutes ago, we go back to the IMDb movies, and this movie review data set, what it does is that it takes the scoring of a movie, and then it gives you the information about the movie, of course, and also the comment that the person left. Okay, so you can see the review that a certain person left. And of course, what we want to do is that we want to take the movie review as it's written and try to determine what was the score that was given to the movie. Okay, so what you're going to do is that you're going to take BERT, right? BERT as a tokenizer. Okay, so what does the tokenizer do? It looks at the sentence, and it breaks the sentence into different tokens, and then it gives the different token, right? So an example, it's here. So this is the sentence, right? So if you give this, you see that it will break down the sentence into this different tokens, and then it will give you an embedding for each token. Then what you're going to do is that you're going to take the embeddings, you're going to sum the embedding over all the tokens, and you're going to obtain the vector. And then you're going to use this vector to do the sentiment prediction. So you have to predict what is the score that was given to the movie, and maybe, if you can figure out what type of movie it was, and so on and so forth and so forth. Of course, the most important thing is for you guys to try to understand how BERT embeds semantics. So there is a little bit of clustering for good and bad words for different aspects of the language, so on and so forth. And then what you can do is that you can do a little bit of fine tuning. Okay, so as we said, these models they are usually need to be trained over a very large set of English corpora, right? Because they do a very difficult job, and the only way to do a difficult job for a machine learning model is to have a lot of data to do this job. But what you can do is that you can try to fine tune the model. So not train from scratch, but just modify the weights slightly. And you can do that by doing the following. You have your model that does the classification of the sentiment. And then ahead of this, in front of this model, you have your BERT embedding. And what you do is that you unfreeze the BERT model and you do a little bit of fine tuning. And so you can experience what does it mean to take one of these very large models and fine tune one of these very large model using only fine tuning. Okay. So when you do the fine tuning, try to learn about it, okay? Because since the advent of LLMs, fine-tuning has become a very important topic, right? Because these LLMs have a gigantic number of parameters, and people don't want to train from scratch, never train from scratch. So what you want to do is that you want to have some very cheap strategy that lets you fine-tune, let's say, an LLM agent with a very little computational power, so that you can personalize your LLM agent on your home hardware, right? So the magic word here is LoRa, low rank adaptation. So a lot of resources, a lot of code has been written for this fine tuning. Yeah, some code snippets here, blah, blah, blah. And then you investigate the performance of the fine-tuned model. And what you want to do is that you want to visualize the largest positive reviews, the largest negative reviews, so you can really see if the model is performing well. Then yeah, you can try to cluster the sentiment of the reviewers, so you can try to understand something more subtle than just a score. If there is some particular use of the language, right? So, for example, there is somebody that really like horrors. So there is so they write about horror movies with a specific language, right? So maybe this shows up in the embedding. So all nice stuff that you guys can discover. Yeah, and that's about it. I think that's about it. I think it's a very fun. It's a very fun challenge, and there is a lot of things to do, and there's a lot of stuff to discover and to observe, right? So it should be pretty exciting. Okay, very good. Anything else, guys? Any other comments? Otherwise, I'll let you guys go, and we update next week. And yeah, I'll try to post the challenge as soon as possible, so you can have as much time for the challenges as possible. And then I propose that we run together in 2-3 weeks, maybe, so that we can give you some extra points for running with me. Of course, if you can run faster than me, you always get 20% improvement in the grade. So that should be your target. Yeah, and otherwise, I'll see you guys soon, okay? I'm going to be here. If you have any question, I'm going to stop the recording now. So goodbye to the people on YouTube. Please like and subscribe and leave a